In this lesson, we examined some of the features of the SN1 reaction, just like we examined some of the features of the SN2 reaction in a previous lesson. So the general principle is that for the SN1 reaction to take place, the energy barrier leading up to the carbocation intermediate must be small enough that the reactants can get up it. If you recall back to the lesson on energy diagrams, the energy diagram for the SN1 tends to be larger than the energy barrier for an SN1 tends to be larger than the energy barrier for an SN2 reaction. Okay, so what features allow this to happen? First of all, the carbocation must be stable enough to exist. So in a previous lesson, we examined the factors that contribute to carbocation stability, and we came to the conclusion that for an SN1 reaction, the carbocation must be tertiary or resonance stabilized secondary. The second factor is the solvent. And for an SN1 reaction, we need the solvent to be a very polar solvent. Why is this? Because this reaction generates ions. Okay, you have the carbocation, but then you also have the anion that's generated upon loss of the leaving group. You generate ions from neutral starting materials. Well, in general, that's not a very favorable process, unless you have a big payoff in terms of acid-base phenomena. Ions are more stable in more polar solvents. So what is a sufficiently polar solvent for SN1? Well, there's actually, I'm going to introduce to you at this point another set of terminology involving solvents, and that's protic versus aprotic. Protic solvents are solvents that have an acidic hydrogen. And when I say an acidic hydrogen, I don't mean a superacidic hydrogen. I mean something that is at least as acidic as water is. So water is on the list of protic solvents. That's a great solvent for SN1 reactions, assuming that your organic starting material, your alkyl halide, for example, is soluble in water. Many organic halides are not soluble in water, which would make water by itself a poor choice as a solvent for such a reaction, even though it's polar. Methanol is not quite as polar as water is, but it is the most polar alcohol. And many organic compounds that don't dissolve in water will dissolve in methanol. So methanol is also a good solvent for the SN1 reaction. If you still have solubility problems, another option for a solvent is to use a mixture of ethanol and water. That is generally should be at least 50% water. So whichever one of these solvents is sufficiently good as a solvent for the starting materials would be a good solvent to carry the reaction out in. There are a couple of other solvents that we think of when we think of really polar solvents, and those would be DMF, which is short for dimethylformamide, or DMSO, which is short for dimethyl sulfoxide. These are called aprotic solvents because they do not have an acidic hydrogen. And these solvents, you can do an SN1 reaction in them if you really need to, but SN1 reactions are actually much faster in protic solvents that are polar as opposed to aprotic solvents which are polar. These polar aprotic solvents are actually excellent choices for doing SN2 reactions, although SN2 reactions are not nearly as sensitive to the solvent polarity as SN1 reactions are. Okay, third feature of this reaction is that you actually don't need a really good nucleophile like you do for the SN2 reaction. And the reason is because the carbocation is so hungry for electrons, it is so desperate, that even nucleophiles that I gave a C to in my lesson on nucleophiles are good enough for SN1. And that means some of the nucleophiles are going to be neutral molecules, and in a subsequent lesson we will see what has to happen for a neutral molecule to be a nucleophile in terms of adding an extra step to the mechanism. The fourth feature is that of stereochemistry. If your alkyl halide is chiral, the product will be a racemic mixture, even if a single enantiomer of alkyl halide is used. The term that we use to refer to this phenomenon is loss of stereochemistry. So what do I mean by this? Well, first of all, think back to the SN2 reaction where we said if you have a chiral alkyl halide, the result is inversion of stereochemistry. So an S starting material would exclusively be converted to an R product. Now, in this case, if we start with a chiral alkyl halide, and there will be lots of chiral alkyl halides that can participate in SN1 reactions, because in general, we're going to be talking about tertiary alkyl halides participating in the SN1. So this is an example of a chiral one. The carbon bearing the leaving group has a methyl, an ethyl, and an isopropyl group. As drawn, this molecule has the S configuration. The bromine is coming out towards you, and the methyl group is going back away from you. So let's say we want to react this alkyl halide with water, which is a sufficiently good nucleophile to react in an SN1 mechanism. What happens first? Well, the first thing that happens is we generate the carbocation through loss of the leaving group. And the point that I would like to make is that carbocations are planar. Okay, this is a simpler model. But because they're planar, when the nucleophile is coming in to attack the carbocation, it's not going to attack from within the plane of the carbocation because there's a lot of steric hindrance in the way. The place where there is available space for a nucleophile to attack is either from above the plane of the carbocation or from below the plane of the carbocation. Okay, so how does this play out? Well, if water attacks from the top face, the initial product is that you have the entire water molecule bound to what was previously the cationic carbon, but notice that the water has a wedge on it because it is bound to the top face. In a future video, we'll cover the details of this, but in a subsequent step, the OH2 plus loses a hydrogen to give a neutral product in which we have an alcohol, and the OH is still on the top face and still has a wedge. Okay, so the OH has replaced the Br in this case with the same stereochemistry. So if we started out with S, we still have S. However, what if water attacks the bottom face? If water attacks the bottom face, now the OH2 plus has the dashes showing that it's below the plane of the page. This pushes the methyl group up because we're now generating tetrahedral geometry out of trigonal planar geometry, and then this stereochemical relationship is maintained upon loss of the proton to give the product. So in this case, the configuration is R. So there is an equal probability of water attacking the top face or the bottom face. It can't tell the difference. It doesn't know which way is up. If it's attacking this face of the carbocation suddenly turns upside down, well, now it's attacking the top face. So because there is an exactly equal probability of attacking either face, and top face attack gives you the S stereochemistry, but bottom face attack gives you the R stereochemistry, you will have exactly a 1-to-1 or racemic mixture of the R and S enantiomers.